Hello viewers, this video lecture is for the subject Theory of Computation and for the topic Pushdown Automata from the third unit. Objectives are to understand the concepts of pushdown automata automation and to design a pushdown automata system for the given language. Now let us see what is meant by pushdown automata. Pushdown automata is one of the implementation mechanism for a given context-free grammar. So previously we have studied about DFA, deterministic finite automata. It is one of the automation model. We can design a DFA for a given grammar. Similarly, PDA is one of the automation model. We can design PDA, pushdown automata, for a given context-free grammar. But there are more differences are there in between the DFA and pushdown automata. A DFA can only remember a finite amount of information, but a PDA can remember an infinite amount of information since PDA has one extra memory, that is external stack memory. So with the help of the stack memory, here, a last in first out memory management capability is available in pushdown automata so that the pushdown automata can store an unbounded amount of information on the stack. Then a PDA can push an element onto the top of the stack and pop off an element from the top of the stack during the course of computation. And to read an element into the stack, the top elements must be popped off and are lost. Now there are some more features are there, like a PDA is more powerful than FA. Any language which can be acceptable by FA can also be acceptable by PDA. Then additionally, PDA can accept more number of language, more class of languages even which cannot be accepted by FA. So PDA is much more superior to FA. Now we can see the PDA structure, PDA automation model. So the PDA system consists of a finite control. Finite control is nothing but it is the unit of computation. Then there will be the input tape. Input tape will store the sequence of input symbols that will be consumed to the finite control. At a time, a single input symbol will be consumed to the finite control, and during the course of execution, some symbols will be pushed onto the stack and something will be popped off from the stack based upon the language and its structure. And finally, it will be decided that whether the input is acceptable or rejected. The input tape is read-only, and it may only move from left to right, and it can consume one symbol at a time. And finite control has some pointer which points the current symbol which is to be read. And already we said the stack memory can push or remove the items from the top of the stack one by one. The stack has an infinite size, so the stack is used to store the items temporarily. Now we can see the formal definition of PDA. PDA can be defined with the help of 7 elements, 7 components, or we can say 7 tuples. Capital letter Q is the finite set of states. This is similar to the definition, the components of DFA. Then sigma is the set of input symbols, or here another one symbol is there, that is the stack symbol. It is otherwise called a stack alphabet. It consists of set of stack symbols, okay, which can be pushed or popped from the stack. Then Q0 is the starting state. Then Z is the starting stack symbol, which is one among the stack alphabet. Okay. Then capital letter F is same as in DFA, which denotes the set of final states. Then delta is the mapping function, which is used for moving from current state to the next state. Always this is the common term that we will use in the DFA. Delta is the state transition function. Now we will represent the state transition of PDA with one representation called as ID representation. ID means instantaneous description. So it is the informal notation of PDA, it will represent how a PDA computes an input string and make a decision that whether the string is accepted or rejected. An instantaneous description will have three parameters: q, w, a. Q describe the current state, and w is the set of string, it is the string or remaining input, and a is the stack component, stack content, that is the stack symbol which is present in the top of the stack. Now we will use some more symbols, notations, while mentioning the instantaneous description, and these two notations will be there. These two symbols are called as turnstile notation. The first one is used to describe one move, and second symbol with the star is used to describe a sequence of moves. This is an example for instantaneous description for a particular PDA. Here P, B, T tends to Q, W, A. It means this will represent one state transition, that is during this transition the system is changing from the state P to Q, and by consuming the input symbol B, small letter B, and the top of the stack, it has currently the top of the stack symbol T will be popped, and the new symbol A will be pushed onto the stack. Okay, so these parameters will represent what are all the things happening in the during the state transition. That is, system is current state is P. In this state transition, system is moving from P to Q by consuming the input symbol B, and the stack structure will be in the current state the top of the stack has T. Now as a result of the state transition, T is replaced by A, that is T will be popped off, and in that place A is pushed onto the stack. Now we are going to see the design of PDA problem. Design a PDA for a particular language A power n, B power 2n, n should be greater than or equal to 1. So first of all, there will be the logic for solving the problem. We have to assume the logic. So the solution mechanism is, in our language our string will has n number of A's followed by 2n number of B's. So we can tell the examples like we can take n equal to 2, then our string will be A power 2 B power 4, A power 2 B power 4. So what will be our string? A B B B B. So for any number of A's we will have double number of B's. So the concept is, if we read a single A, it will push 2 A's onto the stack. Our logic is, if we read a single A, so we have to, at the same time we have to assume our string. What will be our string? For example, I told you A B B is one of our example string. So our automation model is, our logic is, if we read a single A, we will push 2 A's onto the stack. Then after that, if we read B, for every single B, one A will be popped off from the stack. So whenever we receive the input symbol, if the input symbol is A, 2 A's will be pushed on to the stack, and after whenever we receive B symbols, all the A's available in the stack will be removed from the stack, and finally the stack consists of only Z. Z is the default starting symbol of the stack. So when the stack reaches the empty state, that is when the stack has no A's and B's, only it has Z, we will assume the system reaches the final state. So initially we can represent these kind of state transition operations as del of Q0. Initially we will assume the system starting state is Q0. So del of Q0 A Z. So initially the stack will has only Z. Okay. So when we apply a first A to the stack, 2 A's will be pushed on to the stack. So what will be the stack structure? A Z. That is, from the top position the symbols will be A, Z. Last symbol will be in the stack is Z. So for receiving A, the system remains in the same state Q0. Okay, so del of Q0 comma A comma Z equal to Q0 comma AA Z. Similarly, del of Q0 comma AA. So after for the second time when we receive A, previous symbol, the top of the stack consists of A. So now again 2 A's will be pushed off to the stack. So what will be the stack structure? A. The last A is the previous element that is already available in the stack. So when we consume A, when we apply A to the starting state Q0, 2 A's will be pushed on to the stack and the system remains in the same state Q0. Then when B is consumed onto the system, the system will perform the state change. That is, system will change from Q0 to Q1. At that time, the stack operation is the simple A present on the top of the stack will be popped off. That is, definitely the top of the stack consists of A. The single A will be popped off from the stack and nothing will be pushed onto the stack. This is the mechanism. So this will be represented as del of Q0 comma B comma A equal to Q1 comma epsilon. That means when B is applied to Q0, when first time B is applied to Q0, A will be popped off, one A will be popped off from the stack and nothing will be pushed. So there will be no symbol pushed onto the stack. This will be represented with epsilon. No push operation will be represented with epsilon. So the state change is now Q0 to Q1. Input symbol is B, popped symbol is A, and no symbol will be pushed. So we will mention epsilon. And whenever we consume other B's, the system will remains the same state Q1. Here the same operation will be performed, that is for all B, whenever we receive B's, all the remaining A's in the stack will be popped off and nothing will be pushed. System remains in the Q1. So we should understand, for the first time system receive B, system will perform the state change from Q0 to Q1, and after that for each remaining B's, system will perform the popping operation of A simple, popping A simple, and system remains in the same state Q1. Then finally, if all the A's are removed from the stack, at last the stack has only Z. Then all the input symbols get finished. So no input symbol will be applied onto the state Q1, and if the top of the stack consists of Z, in that situation we will reach the final state Q2. So this will be represented as del of Q1 comma epsilon comma Z equal to Q2 comma epsilon. That means onto the state Q1, no input symbols get finished, so no input symbols will be applied, so epsilon, and the top of the stack consists of Z. At that time the system is moving to the new state Q2, which is nothing but the final state, and also nothing will be pushed on to the stack, so we will represent epsilon. So this is our system design. So Q2 is the final state. Now we can define the PDA with the help of the formal definition. We have to list out all the elements. First of all, we have to mention the set of states. Our system has only 3 states, Q0, Q1, Q2, 2 input symbols A, B, and the stack symbols are A, Z. Since B will not be pushed on to the stack, isn't it? So the stack alphabet consists of 2 symbols A, Z. Delta state transition function. Starting state is Q0. Starting stack symbol is Z, and the final state is Q2. So this is our PDA, final PDA. And finally we can summarize the IDs, that is we can summarize all the set of state transition functions for the given PDA as a result. So already we have told about the state transition functions, and one more time we have summarized all the IDs, that is how the state transitions are performed from Q0 to Q2, how the inputs, whatever things happening in the happening by the consumption of A's and B. We should remember, when A is consumed, A will be pushed on to the stack. When B is consumed, all the pushed A's will be popped off from the stack. When stack gets empty, we will reach the final state. So in this way, we have to design a PDA for a given language. Now there is the possibility to check a string onto the PDA whether the string is acceptable or not. So we have to apply the string in the delta function, and we have to consider one by one symbols. We have to apply one by one symbols to the current state, and in the next step we have to mention the new state. What will be the new state after applying the current symbol to the previous state. For example, if we apply A to Q0, there will be no state change. The system will be in the state Q0. Then we can see when we consume B. So we will mention the full string in this operation, but we should consider the first input symbol for the application of delta function. So we should consider of applying the first input symbol in the string to the current state. For example, when we apply B to Q1, what will happen? The A will be, number of A will be reduced from the stack. So when we apply A to the state, A's will be pushed on. A's will be added to the stack. A's will be pushed on to the stack. So when the stack reach to only Z symbol, this will leads to the final state. So if we are able to produce the new state Q2, we will say the given input string is accepted. In this way, we can have the problems in Pushdown automata. Now we can see the possible university questions. Explain the concepts of Pushdown automata with example. Design Pushdown automata for a given language. Thank you all.